Good morning to one and all. In the previous video, we covered up to uh, Harvard versus Van Neumann architecture. Okay, now we are going to differentiate the Harvard and Van Neumann architecture. So the major differences between the Harvard architecture and the Van Neumann architecture are: in Harvard architecture, we use separate buses for both instruction and data fetching. But whereas in the case of Van Neumann architecture, we can use a single bus for both instruction and data fetching. Here, easier to pipeline, so high performance can be achieved in the case of Harvard because we have two separate buses for both instruction as well as data. Here, low performance compared to the Harvard architecture. So it is, according to the cost, the Harvard architecture is very high. So it is cheaper. Van Neumann architecture is cheaper. So no memory alignment problems because separate memories for both instruction and data, but here allows self-modifying codes. So another difference here is since data memory and program memory are stored physically in different locations, so no chances for accidental corruption of program memory. But here, since data memory and program memory are stored physically in the same chip, there is a chance of getting accidental corruption of the program memory. So these are some of the differences between the Harvard and Van Neumann architecture. The next topic here is the big endian versus the little endian process. Okay. Now, what do you mean by endianness? So the endianness specifies the order in which the data is stored in the memory by the processor operations in a multi-byte system. So that means if a system is having more than one byte, okay, we call that system as multi-byte system. Okay, how do we store the data in the memory, or the order in which the data is stored in the memory? That is called endianness. Okay, now if the word length is 2 bytes, okay, then the data can be stored in the memory in two different ways. The first one is called the higher order of data byte at the higher memory location and the lower order of the data byte at the location just below the higher memory. That is one possibility. And another possibility is lower order of data byte at the higher memory location and higher order of data byte at the location just below the higher memory. Okay. Now I'll take one example here. Now I am taking 2579H. Okay. So this is a 16-bit number. Okay. This is 1 byte and this is another byte. And generally we call this as lower byte and this as higher byte. Okay. Now the higher order byte at the higher memory location, and the lower order byte at the just below the higher memory location, preceding that higher memory location. Another possibility is the lower order data byte can be stored at the higher memory location, and the higher order data byte is stored at the location just below the higher memory. So the first one is called the little endian and the second one is called the big endian. Okay, so little endian means the lower order byte of the data is stored in the memory at the lowest address and the higher order byte at the highest address. So the little end comes first. Big endian means the higher order byte of the data is stored in the memory at the lowest address and the lower order byte at the highest address. The big end comes first. So the first one is called the little endian and the second one is called the big endian. Okay. Now see the difference here between big endian versus little endian. So byte 0, byte 1, byte 2, byte 3. Okay. So this is little endian. Okay. Now, so byte 0 is stored at the first address. Byte 1 is stored at the next address. Byte 2 is stored at the next address and byte 3 is stored at the last address. That is called little endian. Big endian means byte 3 is stored at the first address. Byte 2 is stored at the base address. So if this is the base address plus is 1 is nothing but 0x means that it's a hexadecimal number 20001, and the last first byte 0 is stored at the last address, that is 2003. Okay, so this is the little endian versus big endian process. Okay, next one, the load store operation and instruction pipelining. Okay, so the RISC processor instruction set is orthogonal. We discussed it, and it operates on registers. The memory access related operations are performed by the two special instructions. The first one is load, and second one is store. If the operand is specified as memory location, the content of it is loaded to a register using the load instruction. So that means load means the data is already stored in the memory at one particular location. If you want to retrieve that data from the memory location, so you can use the load instruction. So that means copying the data from memory location to the register is nothing but load instruction. So store is nothing but what? Stores the data from a specified register to a specified memory location. Now this is the diagram which illustrates the load and store operations. Okay, so load R1 comma X here. Now what do you mean by load R1 comma X? X is the memory location. The memory location is having some data, so that data will be copied into the register R1. Load R2 comma Y means that the Y is having some memory location. Y is a memory location which is having some data, so that data will be copied to the register R2. Add R3 comma R1 comma R2. It's a 3-operand instruction. So that means add the contents of R1 with R2 and place the result in R3. Okay. Now finally store R3 comma Z. So the result is in R3. You need to copy that result from the register R3 to the memory location Z. Okay. So X to R1, Y to R2, and R1 and R2 will be given as an input to the ALU, and the ALU performs the arithmetic operation, add operation, and finally we keep the result in R3. Okay, so from the R3, the result will be stored to the memory location Z. Okay, so this is about the load, store, operation, and instruction pipeline. Hope you understand this video. We will come with the new content in the next session. Thank you, one and all.